basically providing a similar introduction to what I provided to the O'Reilly conference about a week ago. So basically thinking about what Ethereum is, both from a cryptocurrency perspective and from a perspective of what it's actually meant to accomplish. So, how many people know about Bitcoin here? Okay, maybe about half. So, yeah, how many people know about this blockchain thing that Bitcoin uses? So
3 weeks in. This is the 4th week.
So what is a blockchain?
It's a data structure.
The transaction ledger.
Okay. Yeah, that's one way of describing it. So what's the point of a blockchain?
Trust. Immutable.
So
Single source of shared truth.
Single source of truth. Thank you. That's basically roughly the definition that I was going to go towards. So basically, a blockchain is a way of maintaining distributed consensus on the state of some particular database, is my sort of formal technical definition. So in the case of, all these different decentralized platforms, you have some, whether it's Bitcoin or potentially even Litecoin or colored coins, they all each have so all these sort of systems, they all have some concept of the current state of the system. So for example, in the case of Bitcoin, what the current state is basically just a mapping of which address owns how many Bitcoins. Now, of course, in practice, it's a bit more complicated with unspent transaction outputs, but just to simplify, it's just a table that says this address has 100 BTC, this table has 375 BTC, and so forth. Now,
your slides are progressing rapidly.
okay, so and now also in Bitcoin there's a concept of a transaction. So what does a transaction do? A transaction basically processes some modification to the state. And the idea is that when you take a transaction, the transaction by itself doesn't state exactly how you modify the database. It just provides some kind of instruction. And there is some special mechanism that's agreed to in the protocol of how that instruction is supposed to translate into a change in the database. So in the case of Bitcoin, a transaction says, "Hi, I'm Alice. Here's my digital signature. I want to send 50 BTC to Bob." So in reality, that's in the transaction in Bitcoin, it's actually just a bunch of data fields. But you can, in terms of what those data fields mean, you can think of it like that. Now, then what happens to the database after a transaction gets processed? Well, it's pretty simple. First, we check if Alice actually has 50 Bitcoins. If Alice has less than 50 Bitcoins, then the transaction is invalid. If Alice has at least 50 Bitcoins, then in the database, we take the number that's beside Alice, we subtract 50 from it, we take the number that's beside Bob, we add 50 to it, and potentially you also take off a fee, and that's basically it, you're done. And of course, if the transaction wasn't actually signed by Alice, then that also means the transaction is invalid. So in general, you have a database, then you have some set of transactions, and there is a concept of whether or not a particular transaction is valid. If that transaction is invalid, then it's invalid, you can't do anything with it. If the transaction is valid, then there is some mechanism, some state transition function that tells you what is the database, what is the state going to look like after the transaction gets processed. So over here, you have a bunch of blocks. Each individual block contains some set of transactions. And at the end of a block, there is some state which is somehow updated from the state at the beginning of a block. So basically, in Bitcoin, it's really not that difficult. You just have, the database keeps track of how many Bitcoin everyone has, and if you want to remove some BTC, then, or if you want to send some BTC, then it subtracts it from your balance, adds it to someone else's, and that's basically it. Yes? Yeah, hold on. Just trying to look through what's better to describe it here. There we go. Actually, better set of slides to describe this thing. So, in general, so you can describe the state of the system as being, so in Bitcoin, state of the system is the set of all unspent outputs, how many coins everyone has, and a transaction modifies the state. So this is basically the Bitcoin model. Now the key part that we want to start off with first is trying to figure out how do we generalize the Bitcoin model. So can this kind of model be applied to other applications as well? So first, here's the second use case. Well, let's talk a bit about Namecoin. So Namecoin is a blockchain-based decentralized application. Namecoin also has a decentralized database, and the point of the blockchain is to keep track of the status of that decentralized database. And but here, the decentralized database has a different purpose. So in the case of Bitcoin, the database just records how many Bitcoins everyone has. Now, what does the database do in Namecoin aside from that? Yes?
It's a DNS.
Yes, it's a DNS, meaning what does it have to keep track of?
It's resolving domain names to wherever it resolves to.
Right, so it keeps track of a mapping between domain names and IP addresses, just to put it simply. In reality, you'll probably have a bunch of other records, you'll have owners and so forth, but this is just a simplified model. So over here, once again, we have a database, we have transactions, and we have this concept of a state transition function. And so what do we do here? Well, if I want to make a transaction, and that transaction registers a domain name, then the first check is, of course, do I have enough funds to pay for it? If not, then it's invalid. The second check is, well, is the domain that I'm trying to register already registered? If it is, then it's a fail again. And then finally, if the transaction is valid, then it actually adds the domain that you're trying to register to the database. So, what's the point of this? Blockchain-based domain name registry. Take all of the nice little benefits of decentralization that everyone loves about Bitcoin and bring them over to the world of DNS.
You can also register the public key, right? You can register the public key associated with the domain.
Yeah, you can. Right. Yeah, this is a simplified model. You can also register public keys. I think yes.
So in this model, who would actually validate if an entry is right or not? Not that if it didn't exist or not, but
So in the case of Bitcoin, let's say that I create so first of all, there exists some common concept of what kind of transactions are valid and what kind of transactions are invalid, right? And any client, given a particular state, can determine whether or not a transaction is valid, and if it is, what the new state should be. So in Bitcoin, when you receive a block, and that block contains some transactions, and obviously that block points to some previous block, and you already know what the state is at the end of the previous block, then when you process the transactions, there is a possibility that you'll find that one of the transactions is invalid. If it is, then you reject the block is invalid, and you don't do anything, and you don't update anything at all. Second option is, well, what if all the transactions are valid, then you personally process through the transactions and determine what the state is at the end. So basically, like every node on the network does all the validation for itself, is the way the cryptocurrencies work. So in Bitcoin, that process is applied to transactions. In Namecoin, it's the exact same process, except the functions that you're using are different. So instead of the nodes just validating that you have enough Bitcoin to send, the nodes also validate that you have enough Bitcoin to send, and if you're trying to register a domain that hasn't yet been registered. So, Ripple, another example of a ledger. So here, instead of just keeping track of balances, we also keep track of this concept of trust lines. And the idea is that the whole point of the Ripple ledger is that people have the ability to sort of have debts to other people, and the register just sort of a kind of accounting table for those debts. And so here, the state transition function is, once again, it's pretty similar. If you want to send a transaction to someone, now this time, the difference is that your currency balance is allowed to go below zero, but it's only allowed to go below zero where the amount that A owes B is only, or the amount that A can claim from B can only go below zero if A trusts B to pay him back to a certain extent. And A has the ability to set a transaction to set how much A is willing to trust B. And if A only trusts B with $100, and a transaction is trying to from A is trying to take $1,000 from B, then that's going to be invalid in this context. So all these things, the general idea behind Ethereum is basically to try to generalize this whole concept as much as possible. So instead of having a ledger where the database is supposed to have a specific meaning and there exists some application-specific state transition function that manages that's specialized toward managing some particular thing, whether it's money or domain names or trust lines or whatever else. We have is basically sort of combining a blockchain and a programming language. So the description, the sort of the intuition that I sometimes provide is, back in the 1980s, You would have a separate device for listening to music, you'd have a separate device for reading books, or actually you'd have books back then, oh god. Then, you'd have some separate device for accessing the internet, a separate device for being a phone, and so forth. Now we have a smartphone. Smartphone does everything, except the smartphone has a programming language. In Android, it's basically Java, or you can use C++ as well. In iOS, it's Objective-C or Swift, I think is the latest one. And so people accuse us of overload when we created Swarm when Swarm already exists. Now Apple's created Swift when the Society for Worldwide Interbank Financial Transfers already exists, so no one's really big claiming that.
I actually don't think Apple has as many programming languages as Ethereum does.
Maybe. LLL, Serpent, Solidity, Mouton. Maybe. And JavaScript, I suppose, but that's not always where you use it. Anyway, so the point is that in any of these programming languages, you write an application. Writing an application is thousands of times easier than creating your own appliance. And if someone has one appliance, that appliance can fit like millions of applications. So, that kind of generality is basically what we're trying to bring to blockchain land. So the idea here is you have a blockchain combined with a programming language. So what specifically does that mean? So first of all, the state, it has a concept of accounts. So in Bitcoin, when I was talking about accounts, that's a bit of a simplification because you have these UTXOs. In Ethereum, you actually have accounts. You have in the state, you have this concept of a mapping between address and stuff associated with that address. I believe Ripple works the same way. So what do you have associated with each address? First of all, Ethereum has its own internal currency called Ether. You basically need to have Ether because you need Ether to pay transaction fees. So there's an internal currency called Ether. Then, aside from that, there's two kinds of accounts. The first kind of account is what's called an externally owned account. So externally owned accounts are just accounts controlled by some private key. If your account is controlled by some private key, then if he wants to send a transaction on behalf of that account, the way you do that is you actually produce a transaction, and there's a transaction format in Ethereum, just like there's a transaction format in Bitcoin, and then you sign the transaction with your private key. And then someone else can verify it. To verify the transaction, they verify the signature against the address. And more precisely, they recover the address from the signature, but that's a bit of a complication. So if you just have an externally owned account, then all it has is a balance of Ether, and you have the ability to send transactions, and that's basically it. Now the other kind of account is the more interesting kind. So here, the other kind of account is a contract. So contracts also have addresses, but they have three other things. So first of all, they have a balance. They have a concept of how much Ether they have. Second, they have code. And third, they have an internal database, which we're calling storage. So the sort of last two parts are the most interesting ones, the concept of each account having code and the concept of each account having storage. So the idea with code is that it's, in the Ethereum, there is a programming language. So it's much more advanced and complex than the Bitcoin scripting language. It's basically kind of similar to mainstream virtual machine languages, except it's a lot simpler in some respects. And the way the language works is basically it's very low level. There's a series of opcodes. So there's like an opcode for pushing a number onto a stack. Then there's an opcode for opcode add, which takes the top two items off the stack, adds them together, and puts the result on the stack, and so forth. And then this code has the ability to, it has the ability to like do math internally. It also has the ability to access input and output. So when you send a transaction to a contract, that's when the code associated with the contract runs. In that case, there are opcodes that the contracts can use to input, or to get input. The contract has access to, first of all, some blockchain data like block timestamp, block height, block difficulty, and so forth. It has access to some data from the transaction that was sent into the contract. So, for example, it can access how much, it can ask how much Ether did this transaction send me. Also, each transaction has the ability to send data. So there's a data field, it's potentially unlimited in size, but if you make a really large data field, then you have to pay a very large fee for it. So the contract has the ability to read from the transaction data. So then when the contract, so there's an opcode, so as far as input goes, it can read from the transaction data. It can also read from its internal storage. So the internal storage It's basically kind of a key value map, 32-byte keys, 32-byte values. You can read from it and you can write to it. So if he wants to store things, you would store them in storage. So there are opcodes for reading the storage, there are opcodes for writing the storage, and finally there is also an opcode by which one of these contracts itself has the ability to send, I guess, what we call a message. So a message basically is a transaction, except the difference is that a transaction is something that originates from the outside. It's something that's actually signed by some private key. A message is kind of like a transaction that gets created by a contract. So contracts have the ability to send messages to other contracts, and so contracts can talk to contracts just like external users can talk to contracts. So here, this is just an example of what the state transition function would look like. So in this case, what we have is just a simple name registry. So name registry just uses the key value map pretty simply. It says if the contract storage at the key that you're trying to register is empty, then it sets the contract storage at the key that you're trying to register to the values that you're trying to register. And so the idea is if you want to register some key to some value in this database, then what you have to do is you have to send a transaction to it, or send a message if you're a contractor and trying to register something. And in that transaction, you would put two data fields. The first data field would be representing the key you're trying to register, and the second data field would be representing the value. So you could imagine like 32 bytes for the key, 32 bytes for the value is basically the default in all more programming languages. So then, what happens? Suppose that I have a transaction, and that transaction is from some account that controls some externally owned account that controls some amount of ether. It goes to this domain name registry contract. It has some tiny amount of ether, it doesn't have to. And then as data fields, it has some key and some value. So the transaction gets sent, then because the transaction is directed at this contract, the contract's code runs, and the contract's code accesses the transaction data, and it checks. First of all, has this particular key been registered in my state yet? It looks like it hasn't, therefore I'm going to register the value associated with that key. And that's basically it. So the code runs, and once the code finishes running, that's the end. Now obviously, if this contract is more complex and it ends up calling other contracts, then the execution might get more complicated. You could have a message being sent. You could have a message being sent from A to B, then B would start to send something off to C, D, and E, and then C, D, and E would all run. C might call back to A, and so forth. Now, the important thing is that because it's a Turing-complete programming language, so you have the ability to make a loop. So you have the ability to make code that says while x is greater than 0, add 1 to x, and that'll just keep on increasing x forever. And the other thing you could do is you could have you could set up a contract A which calls B, which sends a message to B and set B up so that its code sends a message to A. So either way, you could try to have an infinite loop where the computation goes on forever. So the way that Ethereum protects against that is we basically say, well, we have this concept of gas. So gas you can think of it as being like you counter of computational steps. So the idea is that when you send a transaction, you have the ability to specify how much gas are you willing to consume for that transaction. And when you specify that, let's say you specify 10,000 gas, then the entire computation that sort of starts going from your transaction can consume a maximum of 10,000 units of gas. So most operations like add and multiply and so forth consume 1 gas. There are some operations that consume more. Now, there's two possibilities. One possibility is that let's say you gave the transaction 10,000 gas. The transaction's computation consumed, say, 1,000 gas, and then it returned. Then what happens? So when the transaction first specifies the gas limit, it also has to specify a gas price, and it actually has to, at the beginning of the execution, it has to pay the gas limit multiplied by the gas price. So if your transaction budgets for itself 10,000 gas and it says I'm going to pay a millionth of an ether for each gas, then the transaction has to initially pay 0.01 ether as a fee. Now if the execution ends and there's a bunch of gas left, then at the end of the computation, the remaining, the amount that you paid for the gas you have left remaining gets refunded. So over here you offered to pay a millionth of an ether for gas, you have 9,000 gas left, so you have 9,000th of an ether gets refunded to you. The other option, of course, is, well, what if your computation takes so long that you run out of gas? So in this case, it's not nice for you. Basically what happens is that all the computation gets reverted, but you still have to pay for the entire gas anyway. So the point of this mechanism is basically so that it's not possible to like do denial of service attacks on miners by sending transactions through them that just run out of gas. Because if you do, those transactions do nothing, but you still have to pay 1 unit of gas for every computational step that the miners took. So all an infinite loop does is it just steals money from you, and that's it. Yes.
So is the gas rate set by the miners, or is it set by?
So the amount of gas that each individual operation consumes is set in the protocol. The amount of ether that you have to pay, the amount of ether that a transaction pays for a unit of gas is set by the transaction. So when you send a transaction, you have the ability to say, I am willing to send 10,000. I am willing to use up to 10,000 gas, and here's the amount I'm willing to pay for 1 unit of gas. And miners have the ability to accept or reject that.
So if it doesn't get mined, then which miner gets all that money? If the transaction doesn't get mined, right, because it never completed, so which miner gets the money?
If the transaction never gets included in the block, then no one ever gets the money, because the transaction never gets included in the block.
So everyone gets the money.
Well, no, the transaction sender still has the money and has the ability to use it for other purposes. Right?
So you can run out of gas where parts of your parts of stuff are included in the chain, and then it still doesn't complete. And then what happens? There's like a new state change that is introduced to bring it back to the original?
No, it's not that. So so one transaction is sort of itself a kind of unit, an indivisible unit of changing the state, right? So if a transaction gets reverted, or if a transaction runs out of gas and it gets reverted, then the thing that gets recorded is that the state after executing the transaction is basically the exact same thing as the state before executing the transaction, except that you lose your money. So, I mean, yeah, the way that it's implemented in the client is either you just sort of hop back to the previous state, or in the more advanced clients, if you're using a journal and cache injection, you have to manually revert a bit, but that's an implementation detail. So
Vitalik,
yes.
In the case where the transaction, the state doesn't change because it's run out of gas, there's a miner that's running that script, and he keeps the gas.
Yes.
There's only one miner doing it, right?
Theoretically, any miner can include a transaction.
Should there be more than one? So do you have to like do
Realistically, if you broadcast the transaction to the network, then you'll have a whole bunch of miners trying to process it, and one of them will make a successful block.
So they're all running these scripts before they actually know if they have the next block.
Well, when they run the scripts, they know that the transaction is going to be valid, right? They just don't know they don't know what the final result will be, but they do know that whatever the final result will be, it'll be profitable for them. Because if it runs out, then they get the fee. If it executes normally, they get the fee.
So they only get the fee if they're the ones that mine the block?
Yeah, I mean, it's just like Bitcoin.
Okay. Yeah. Yeah.
But if there's two miners running a contract and it runs out of gas, they can't both keep the money.
No, the one that includes a transaction in a block that ends up being part of the blockchain makes the money.
But if there's no state change, then
No, but okay, so there is always a state change, but in this case, the state change is just kind of null. All it does is it takes away the money.
Okay.
So, So the idea, so the other important point is, if you have a contract that sends a message to another contract,